Linear algebra, last problem for 6.3. Let W be a subspace of Rn with an orthogonal basis of W1 through Wp and V1 through VQ, an orthogonal basis for W perp. This problem is basically going to talk us through the fact that we can make a basis for Rn by combining the bases for W and W perp. So another way to think about this is that W and W perp together sort of make up all of Rn. So basically, W and W perp combine to make all of Rn, which is really pretty cool if you think about it. So first we want to explain why this set is an orthogonal set. And so we need to show that any two vectors in it are orthogonal. So there's sort of three possible cases. I could take two vectors that are both in W, I could take two vectors that are both in V, or I could take one from W and one from V. So any two vectors that were in W, why are they going to be perpendicular to each other as long as they're not the same vector? Well, W1 through WP form an orthogonal set. So this is true because W1 through WP form an orthogonal set already. And the same is true if I take any two vectors that are in W perp, because we said that V1 through VQ are already orthogonal. They're an orthogonal basis. So if I take one from W and one from W perp, why are they going to be orthogonal? Well, this is because Vj, any vector in W perp, is orthogonal to any vector in W. By definition, any vector in the perpendicular of a subspace is perpendicular to any vector in the subspace. And so in particular, it will be orthogonal to the V's, or to the W's that are in the orthogonal set. Now we want to argue why W1 through WP combined with V1 through VQ spans Rn. So the way that we do this is we pick any vector in Rn, and we want to show that we can get it as a linear combination of the W1s or the W's and the V's. So let's look again at Theorem 8. Theorem 8 says that any y in Rn can be written uniquely as y hat plus z, where y hat is in W and z is in W perp. So if I take any vector in Yn, then I can write it as the orthogonal projection onto W and some vector z, where this one is in W and this one's in W perp. But since the Wi form a basis for W, that means that I can write y hat as a linear combo of the little w's. And since the V's form a basis for W perp, then I can write Z as a linear combo of the V's. And so that means I wrote Y as a linear combination of things made up of only W's and V's. So we're good. It spans. So now finally I want to argue that the dimension of W plus the dimension of W perp equals n. The dimension of W is P, and the dimension of W perp is Q, because these are bases. So basically I can argue this just by showing that Wi combined with the Vj's form basis. A basis has to span Rn, which we showed in part B. So we got spanning, and it has to be linearly independent. But theorem 4 from section 6.2 tells us that if we have an orthogonal set of vectors, that set of vectors must be linearly independent. And A, we proved that they were orthogonal. So since we have a basis, there must be n vectors in it. So that's all for 24, and we're going to work with this idea actually in section 6.4. So keep up the good work and let me know if you guys have any questions.